conversation about intervals. So in sets, things that cover are supposed to tell you where the parameters live. It depends on what type of set I'm talking about for me to have that covered. And so if you haven't caught on, there's two types of intervals. There's the Bayesian ones and there's the frequentist ones. We'll go through the terminology and we have to be really specific. We'll be looking at an example that shows disagreement. I presented to you with this paper, and this is online, so you can download it. Have a look at it. This is a pretty well cited, hotly contested, very agreed upon, not agreed upon at all. People feel strongly about this one. I think it's a good paper to read through all the way through graduate school. Keep coming back to it. Read it. If you don't understand a section or an argument, work on that for a while. It's pretty dense. The examples are all toys in here. I don't know if Jim has the applet that he built for this. We can talk about some of the outcomes from it. But the title, could Fisher, Jefferys, and Neyman have agreed on testing? This is quite intentional to try to upset everybody. So, agreement sounds like a good thing, but when you put three people in a room that could never agree on anything, you're setting up a fight. So, I think it's very intentional. I also enjoy it. So, just as long as everybody's semi-civilized, we'll get to see some of the argument at the end. This paper had a rejoinder attached to it. So people came in, did a critique, follow-up special edition on this paper, people from both camps, or all the camps maybe. Maybe there's not just two camps, but there's a whole spectrum of camps. And they comment on this. That's also included at the back of the paper. There's a lot to read here about testing and intervals. So this paper is specifically about testing. We'll get into some of the testing examples in about a month. So that's the p-value versus posterior conversation. I'll allude to it in here, but this also has the example that we're studying to illuminate some of the basic differences between confidence intervals and credible intervals. In my case, we're not going to construct an interval, we're going to construct a set. Okay? An interval is a set. So it's a type of set, it's not a connecting set. So hopefully that doesn't baffle you too much. The context of the problem sets it up for us to do that. We've already kind of gone through a number of examples. I'm going to switch over and just look at the examples that we looked at last time. And we'll start to carve our way through this. I just kind of rewrote out everything with maybe a nicer picture for you to follow from last time. So, confidence intervals, they're coverage intervals. So this thing, what the idea is that you're giving a stochastic process for generating intervals given stochastic data. And those intervals are designed to cover the truth a certain amount of time. So I think we all know that. What does that mean? Maybe that means good things. Maybe it doesn't mean good things. It depends on the context. I have to admit that if I had a credible interval from a Bayesian, and I was in a situation where I could repeat the process and you did see flurries of data coming around, I might want my intervals to also cover. So that's a personal choice. I might want both things. There have been attempts by Bayesians to construct intervals that are also belief intervals. By the nature of the interval, the distribution is on the parameter. That's where you believe the parameter is. That also cover. All the approaches that can do this in general are highly computational. So there's no set paradigm for doing this. Saying that, we have seen Bayesian intervals that cover very well. Your homework takes you through that. So sometimes you get it for free from some of the objective procedures for developing drivers, but it's no guarantee. And the only methods I know for guaranteeing that you have both simultaneously are very computational. Basically, they build step functions, and they make the distribution, and they wiggle around that distribution until you get them. So then you get coverage. Okay. Not super practical in high heat, virtually impossible to compute that. Okay. So confidence intervals are designed to be coverage intervals. I want to point out that this could be approximate. And usually the key to hearing the word approximate is asymptotic. So as n gets bigger, these get better. How good are they with whatever your data set is could be quite terrible. And in our beta binomial, or our binomial example, where we use the walled interval as a normal approximation, in the middle of the space where p is about 0.5 true p, they cover pretty good. Near the boundaries, we fall apart. Always be aware that if you have things near boundaries, math gets hard, probably your asymptotic methods aren't great. You usually do need regularizers. Bayesians have that built in. Okay, so here's everything we said last time. Example, let's just work with the example that we know best. I kind of hate this example too, because it's so simple that we get too invested on building decision theory that will correctly accept or reject. Maybe I should say fail to reject or reject. But these problems where they're just one-dimensional, my real opinion is just estimate the parameter and tell us where you think it is. Okay, so do confidence intervals do that? Not necessarily. Sometimes they do. This example, I think, does coincide with a case where you might get both interpretations and it happens for free. So it tells us something about the parameter. Saying that this interval wasn't designed to do that. So here's my little picture right here that I get all my xi's. X bar is informative about theta. You can work out the likelihood function. It would be proportional to this. I've normalized it already. What I really did is I used the sufficient statistic. Oops. Sorry, I'm already ahead of myself. This is a distribution on X bar, is really what I want to say. So this thing right here is X, is a function of this random variable. This is the actual number that I computed from everything. So this right here is just sum of the Xi's over. This is my random variable, just so you're not confused. I wrote down two things that are the same. One represents the space, one represents the actual calculation. Okay, so a confidence interval for our normal thing is usually built like this. Right here, I look for the 2.5% tails, everything is symmetric, I chop those off, and then I define my interval by those boundaries. Okay, here's another thing that people sometimes will show you. So they'll say, this is true. This is normally distributed. X bar minus theta over sigma over root n. As a normal distribution, that's not asymptotic because of the nature of the problem. The xi's were normal, so this is exact. If the xi's were not normal and I did something like this, I'd be working in the asymptotic framework. So, but this one's exact. So that really is an equal sign. So very good. So we don't have any of the asymptotic stuff to worry about in this example. Let's just think about it, what people do. So most of you know that the control limits for the 95% interval are 1.96 approximately. So a lot of times I just say 2 times the SV. So I round in my head a lot of times. But 1.96 is close enough for us. What's random in this equation? It's not theta. It's the other one. It's X bar. So keep in mind, we're not Bayesians yet. We're working in the confidence thing. And so X bar is what's random. So this is random. This thing, that's random. It's probability distribution on X bar. That's inducing all the randomness here. So we're kind of thinking about this standardized statistic. Usually people will call that something like Z. your z-score. If I knew what theta is, I just subtract it off. So it's centered at 0, the mean, and I divide by my standard error. X bar is random. Theta is fixed in the classical framework. This thing. That's the distribution on X bar. So what I did is I generated the xi from our normal distribution centered at theta, and then I computed in my head, I know what the distribution on X bar is. So classicist X bar is random. Yeah, this is the distribution. Okay, so this is the distribution on xi's up here, but this right here is the distribution on X bar. Oh, you're saying center visit theta. Okay, I got you.
Like a normal practice, and X bar, the parameter should be theta.
Yeah, you're right. So that's not random. This is centered at theta right here. And X bar is the random thing. For the clarification. Sometimes I don't know. Sure mistake or mine. That's definitely mine. That's theta. So this is the distribution on X bar. That's what's random right here. So I can compute this probability, 0.95, just through our standard normal sort of thing. You look at your Z table. Hopefully you never look at a Z table ever again. And hopefully you never have your students look at it. So we got to move on from that. So I can just rearrange everything. So my rearrangement, just that. So that's called pivoting right there. I pivoted around some statistic. So don't worry about the technical nuances of that. Take inference class if you want to hear all about that. So that's the typical thing that people do. Now you've got theta in the middle. What's random in this equation? Still X bar. We didn't change anything. So this is the confidence string right here. Is that you're feeling like this is a statement about theta, but it's not. This is fixed. So it's still fixed. The X bars are random. So it's the limits of your confidence interval. That's the random bit. And we've said that a whole bunch of times. It doesn't matter how you write it. It doesn't change the nature of the random. Bayesian's a little bit different. We write this down. So here's my distribution on theta right here. I wind up with a very similar expression. Keep in mind I've used the flat problem. So the Bayesian and the classicists come up with the exact same intervals, and we interpret them. So that's everything we said last time. This paper goes into this at length, and comes back around to the example that we're studying. Let's look at the paper for a moment. So Ronald Fisher advocated testing using p-values. Harold Jefferys proposed use of objective posterior probabilities or of hypotheses. And Jersey Neyman recommended testing with fixed error probabilities. Each was quite critical of the other's approaches. Most troubling for statistics and science is that the three approaches can lead to quite different practical conclusions. Now that is true, and there are cases where we coincide. Let me just let the cat out of the bag. Most people agree on estimation. Asymptotically, we probably agree. You know, we want our estimators to be at least consistent, so they converge to the right thing. So usually we're pretty close on estimation. As data sets go up, the size of the data set, we usually converge. Testing is not that way. So, and there's certain types of tests where we disagree. So let's just see if they can tell us anything about this. I'll just read through the results real quickly that I've highlighted, just to give you some idea of what's going on in this paper, because you're going to read through it and probably be a bit puzzled at first. It doesn't get into the confidence stuff for a while. But example one, xi's are normally distributed. Our example, let sigma squared be known. Doesn't really change anything in the problem. If you don't know sigma squared, you can estimate it. We're probably going to estimate it the same way or very, very closely. We're going to move to t-distributions. You are testing. Okay. They give you some specifications on everything. They tell you some numbers so you can do the calculation. So they throw some numbers in that they report what Fisher would have said, what Jefferys would have said in Neyman. So in the context of this problem, and you could work through it, we will do examples exactly like this. So you can hold off too, and I'll do this calculation for you, but it's in like a month. Fisher would report a p-value. Under this situation right here, p-value would be 0.021. He's got a couple different numbers that he's computed just to show you a little bit of the extremity of it. So I'll just read off the first one, 0.021. Jefferys would compute the probability on the null hypothesis, comes up with 0.38.
Just reading it off.
Oh, shoot. You could have done that the whole time. I was just reading the top portion of that. We didn't get very far. So example one, some numbers. Let me look at that for a second. Everything's normally distributed. It's the context of our example. We haven't shown you how to do the posterior calculation for this, so that's where we need to pick up some speed for later. But we'll go through these calculations. Fisher would report the p-value of 0.021. In this case right here, the sharp case, some of you might already know this. This calculation corresponds to a confidence interval. So the confidence interval, what it tells you is the set of values of theta such that the p-value is under 0.05. So it gives you all of those things. Where would you have rejected? Where would you not have rejected? So they can hit it around that thing. My inference class goes into some detail about that. Jefferys would have computed posterior probability of 0.28 under these numbers. All you're supposed to notice from this is it's like over 10 times greater. Very different conclusions. So in a typical classical class, if you haven't seen these examples for a while and you really thought hard about them, Fisher's telling you to reject. What is Jefferys telling you? I do not know in this example. Right here, is that a reject or is that not a reject? That's a non-negligible probability. I will say also, just for those in the back of the room that might be snoozing, that the prior that they used on the alternative space here was Cauchy. So that's very interesting. A non-conjugate prior. We'll go into that and we'll talk about it. But I'm quite proud of Jim for using the Cauchy distribution right here. So good job. That's the one I would use too in this example. So we agree. So what does that mean? I don't know. Neyman, he would do something entirely different from these two. And Neyman, while he would compute the p-value to see if it ducks alpha, and he would report the error probability back to you. So Neyman comes in and says, the answer is 0.05 error. So I'm just telling you my error rate. The p-value doesn't mean anything. Fisher thinks that the p-value is a proxy for evidence against the null. I'm not sure if that's true. We'll get into that example. And Jefferys is building a belief on the null hypothesis. So basically everybody has a different thing to report and they feel quite differently about what should be reported. Interestingly, it was Neyman and Carl Pearson's son, they were trying to do Fisher a favor, I think, with this sort of sharp thresholding at 0.05 and give correct interpretations to things so that you understood what the probability was about. They would probably say, this is the probability of your data, more extreme data, what the heck does that mean about anything? So let's give you an error rate of how long I'm wrong. Fisher didn't like it. So if you like to think about things on a continuum, Bayesian's also thinking about things on a continuum, but very, very differently. So two continuous folks and somebody that's a hard threshold. Saying that, Neyman never did this analysis. Neyman never walked around and said, I'm just reporting 0.05. He was doing math and explaining what things meant mathematically. The discrepancy between the numbers reported by Fisher and Jefferys are dramatic in both cases. While the discrepancy between the numbers reported by Fisher and Neyman are dramatic, primarily in the second case, even if one goes past the raw numbers and considers the actual scales of evidence recommended by the three significant differences we made. So this is an important paragraph right here. The disagreement occurs primarily when testing precise hypotheses as above. So sharp nulls, beta is this number, versus the one-sided thing. I'll just read their words. When testing a one-sided hypothesis, such as beta less than 0, the numbers reported by Fisher-Jefferys and Jefferys would often be similar. That's true. And in the normal case, if you used a flat prior, it would be exactly the same. So the one-sided case in the p-value posterior of the null, and the p-value turn out to be the same numbers. In the sharp null case, we'll get there. It's all related to intervals. No group. So probably the test that everybody's doing too. No group. It's kind of interesting. Okay. There's some approaches. They walk you through the approaches. There's criticisms. So there's even criticisms for Bayesians. You can skim this paper. Let's read their criticism because I think it was Mohammed's question. Criticism of the Bayesian approach. Fisher and Neyman felt that it is difficult and or inappropriate to choose a prior distribution for Bayesian testing. They just didn't like it. Sounds bad, kind of does. So, what do your priors do? So that's the whole thing. Jefferys has this auto way of coming up with a prior. The prior he would have chosen, and we'll go through his math soon enough, is proportional to 1. So he would have used the flat prior. When he does testing, however, cannot do that. And then there's a lot of questions of what is the Bayesian doing? Bayesian's always comparing against things. Get into that in just a second. Okay, so, I don't know, they just didn't like it, didn't want to do it, didn't understand it, stubborn, I don't know what it was. But you would even hear classicists arguing with Fisher about using the likelihood. What is this likelihood business? So, why even do it? We'll get into some passages about that. I think the history is important, especially in these contexts. So, it's important to know that people didn't always get along and agree. So, unlike in our classes where we say do this, do that. So, there's still open debate. Criticisms of Bain and Pearson, it's sharp, it's only telling you the error rate. Also, if your model assumptions are wrong, you're going to have even smaller p-values. Might feel good, like you just discovered something, but possibly what you discovered is your own mistake. So, all very interesting. Criticisms of p-values. There is a quote in here. Neyman criticized p-values for violating the frequentist principle, while Jefferys felt that the logic of basing p-values on a tail area as opposed to the actual data was silly. A hypothesis, this is the fun part, a hypothesis that may be true may be rejected because it has not predicted observable results that have not occurred. Let me read that one more time. A lot of people like to say quotes from Box, all models are wrong. They'll get it tattooed on themselves. They like to say it. If I were to get anything tattooed on me that had to do with statistics, it would be this quote. It cracks me up every time I read it. A hypothesis that may be true may be rejected because it has not predicted observable results that have not occurred. That's exactly what a p-value does. He's just saying it in English. So read through that a couple more times. See if you can massage it into some meaning. But he's mocking the p-value calculation. And he's saying in words exactly what it does. It's quite contorted. That's okay. That's all just fun banter. I'm not saying that you never use a p-value. We'll talk about it when we get to that portion of the class. Conditional frequentist testing. So this is kind of the part that we're studying in our example. And I think it's worth kind of dwelling on. Conditional inference is one of the most important concepts in statistics, but often it is not taught in statistics courses or even graduate programs. In part, this is because conditioning is automatic in the Bayesian paradigm, and hence not a subject of particular methodological interest to Bayesians. So the Bayesian is always conditioning on everything. Here's your data set. Boom. Whole thing. That has all the ancillary statistics in it, all the sufficient statistics, everything. It's the data set. And that's essentially what the likelihood function is. It's a conditional inference on everything. And so Bayesians do not study conditional frequentism. So the conditioning part happens for because it used the likelihood. Boom. Saying that, it's an important concept for frequentists to study. So I always ask, like, what kind of frequentist are you? When people tell me a frequentist, if they don't give me an answer, I don't need to hear it. You know? So if you're just going to mince all your versions of frequentism and not be consistent, you know, maybe it requires a little bit more thought. Okay, here's the example that we were studying last time. We'll come back around to this. And they say, here is a 75% confidence set. They say at the very bottom, this is not at all a sensible report once the data are in. So what they're saying is, of these two answers right here, whatever you report, either the average, that's always theta, right there, or you arbitrarily pick one of the points. X1 minus 1, maybe that's theta. Theta 50% of the time in this setup. So that's overall a 75% interval because these things each happen with probability perhaps. If I change those numbers, those probabilities right here, it would change the coverage. So those are dependent. These numbers determine this coverage level. So 75% of the time, the arithmetic's pretty simple. If you coded this up on a computer, you ran it a whole bunch of times, this thing would converge to 75% of your calculation. Saying that, every time you do this, I guess it's 75%. Terrible answer. So they say in this paper, to obtain a sensible frequentist answer here, one can define the conditioning statistic, the difference between the two numbers. And effectively, if that number is 2, so theta minus 1, theta plus 1, if the difference between those two things is 2, you just solve 2 different numbers, is what they're saying. So they're conditioning effectively when s is equal to 2, they're conditioning on this out. That's the exact same statement. And they might report that the probability when s is equal to 2, the numbers are different. The probability is 1 of theta. So I've given you theta. And the probability is 1. If the numbers are different or the same, that's what this says. So if the difference between them is 0, you just solve the same number twice. Then maybe you report a half. That's also a 75% confidence thing. And this would be a reasonable answer. And everybody likes this answer. The whole point of this discussion is that there's no paradigm for doing this. What do you condition on? How do you condition? Their sample space is on the data in the first place. So you're supposed to take a piece of the data somehow and condition on it. And there's no framework for doing that. They talk about this in this paper that Fisher knew about this. He was very aware. He did condition. Frequentists often condition. There's an example in here where they say frequentists will condition on sample sizes to create weighted averages, things like that, the right thing to do. So I don't want to just teach you MCMs. I want you to understand, the core of this discussion. So there's no paradigm for doing this. They kind of talk about it. They knew that it was important, but there is no established way of coming up with a conditioning statistic. So you can only kind of do it in really simple cases. That's promise. This paper had promise. And I would read through these comments. This paper took me a little while to read through when I was in graduate school. Nobody told me to read it. I just read it. So I think that's a good process, I guess, for you guys going through things. You hear about something, you take the time to read it, and you think about it, what it means. So Ronald Christensen says, I feel privileged to congratulate Jim Berger on his exemplary career leading to the Fisher Lectureship. So this is fascinating. Bayesian is given the Fisher Lecture in JSM. So that's an esteemed lecture. It's a privilege to be able to give that lecture. You usually are congratulating somebody who's had an exemplary career, as Ron Christensen says. He's at University of New Mexico in Albuquerque. You wanted to know who he was. Every time I see these people, I look them up. Who are they? Why do they believe what they believe? What do they do? What kind of problems do they work on? So it's all in the context of that I want to understand why they make their choices. Sometimes they might be good choices, but for other problems, there might be something else. Okay, I totally agree with the premise that there is vast confusion about the practical use of testing. Now, I hope that this article cuts one more nail into the coffin that Neyman and Pearson testing so richly deserves. Boom. What did you just say?
He doesn't like p-values either.
Doesn't like this whole Neyman-Pearson thing. So it's not the p-value, it's the alpha level. So Neyman and Pearson are reporting the error, not just the p-value. So he's taking a strike at Neyman and Pearson. That's a different thing. A lot of people mince these two things. Neyman and Pearson and Fisher did not get along. They're not the same types of people. They're advocating something extremely different. That's right. So Neyman and Pearson say you have to have it. You don't get a budget after you see the p-value. If you do that, it's not right. That's what Jim's applet does. Is it computes for you the actual probabilities if you start, moving your alpha level in different ranges. And says it's not at all what you think is going on. So you don't get to budge the alpha level. That's the whole thing on SAS alpha that they'll give you stars sometimes into things. So you're only supposed to look at stars. But that's even a cop-out because it's like, well, if your alpha level is 0.05, or if your alpha level is 0.1, or if your alpha level is, 0.25, that'd be pretty big. They give you stars for all of those indicators of which category you fell into. So if your alpha level was something, you'd be significant in this at that level. Weird stuff. So, Ron Christensen is saying, yeah, to Neyman Pearson testing. I bet they would get along. So they probably would have a really good conversation about it. So knowing the personalities involved here. Anyway, Ron's pretty congratulatory. Wes Johnson, he's out in California. It's a privilege to comment on the weighty topic of statistical testing. Our profession suffers from a lack of coherence in its philosophical underpinnings. Bad. Real bad. So this whole decision theory thing that we're doing without real loss functions built into everything and contextualizing the problem, this is going to make these statisticians look silly in the future if it hasn't already done it. So I'll just go through a couple more of these because they're fun to look at. Michael Levine is my advisor. So that's not surprising at all. I want to begin by thanking Professor Berger for an extremely well-written and thought-provoking article. Its main points are to explain conditional error probabilities and argue that they can result in methodological unification. So that's what Berger is trying to do, is saying, under what assumptions do we all agree with each other? So, in And then he picks some and then says everybody should actually take it. This discussion will focus on whether conditional error probabilities do in fact provide a methodology acceptable to everyone, and whether such a unification is desirable. So do CDPs resolve methodological issues? His answer is no. And there's a paper that he wrote with Mark Shervish over at CMU that said it basically depends on how you group the alternative hypotheses. And that's the whole point. So he writes a paper. We'll discuss that paper once we get to decision theory. We'll discuss Mark Shervish's first paper on p-values that kind of spawned Michael Levine's article. We'll talk about that. Basically, Michael thinks he didn't do anything here. It's more a bunch of mathematical parlor tricks, and beta factors can also have issues. I think he's right. So let's just read this part. It seems CPs will not be attractive to subjective Bayesians or to anyone who values coherence. That's a very important word right here. So in the meantime, I'm not trying to figure out what that means. I will be discussing it when we get to p-values. They're not coherent in the show case. And they will not provide methodological unification between such people as Jefferys and Neyman. I'll work on that myself. So he says no. So Michael's on to him. There's no unification. This one, similar. Discussing a philosophical paper is always tricky business. So he ends up saying that he's basically going to argue against Jim's cases, but he likes the examples for spurring conversation. Lots to read in here. Deborah Meyer, she's the final discussant on this paper. Does anybody know who she is? She's the professor of Virginia. She's in the philosophy department. She's now emeritus. She lives in Ellen Valley. Very interesting person. She does not, her and Jim get along because they're professionals. That's all. So she's always arguing. Okay, this is the most interesting discussion, I think. I'll just read to you a little bit. When two or more methodologies of inference recommend different appraisals of evidence, there are two broad avenues that might be taken to reconcile them. The first is to take the position that the conflicting methodologies operate with distinct aims, goals, and assumptions. And that rather than insist that one or both be embedded to achieve unified appraisals, one should articulate the intended interpretation of the key components of each so as to avoid confusions and clarify the different domains in which one or the other methodology might be most appropriate. The second position is to maintain that one of the methodologies, say M1, is superior or more plausible. I'm going to end that right there. What she's saying is basically you could put one camp into the other one or the other one into the other one. I kind of find it interesting that she uses the word avoid confusions. I've never read anything more confusing. So her comment section when I read it, could not understand what she was talking about. I get it now. I went to Jim, I asked about it, and he roughly explained it to me. So what she was talking about. Anyway, she says you've changed the word error probability, you've changed all of what probabilities we're talking about, but that is the confusion. Is what probabilities are we talking about? What are the error probabilities? So let's go back to an example from this paper that highlights the distinction between frequentists and Bayesians. Hopefully that's thought-provoking for you. If that isn't, I have another passage for you that I'll just read real quickly before we go through this. We've seen an example where everybody agrees. This book is The Lady Tasting Tea. So this is a University of Connecticut professor. The part that I find most hilarious about the book is the word modern. Don't use it when you write. Do you know why? Modern. Bingo. So Don't use the word the new one. So, because it doesn't last for long. This was written in 2001, and there's a lot of things that he talks about as being modern, and I just always get a good chuckle. So, that's okay. Okay. There's a chapter in this book called The Confidence Trick. This is chapter 12. Confidence trick, you can zoom in right there. So, it's basically that pivot thing. What's random, what's the probability? But this gets a lot of discussion. Okay, let's see if I can see this. Okay, there was a discussion of Neyman's original paper on all of this. And he kind of came to the floor, he was chairing a workshop on this, and he wanted to talk about everything that he understood. Professor G.M. Bowley was in the chair for the meeting and rose to propose a vote of thanks. He first discussed the main part of the paper for several paragraphs. Then he got to the appendix. So, he says, thank you for doing all of this. I've read your 4 lines. I've studied it carefully. I think I might understand, but here we go. I'm not certain whether to ask for an explanation or to cast a doubt. It is suggested in the paper that the work is difficult to follow, and I may be one of those who have been misled by it. Later in the paragraph, he works out an example showing that he clearly understood what Neyman was proposing. Humility, it actually kind of works. I wish I had more of that. I can only say that I have read it at the time it appeared, and since, and I read Dr. Neyman's elucidation of it yesterday with great care. I'm referring to Dr. Neyman's confidence limits. I'm not at all sure that the confidence is not a confidence trick. So he points out. Foley then works out an example of Neyman's confidence interval and continues, does that really take us any further? Do we know more than we knew previously? Does it take us beyond Carl Pearson and Edgeworth, a leading figure in the early development of mathematical statistics? Does it really lead us towards what we need? The chance in the universe which we are sampling the proportion is within a certain limit. I think it does not. Do you not know that I've expressed my thoughts quite accurately? It goes on and on. It gets to this is the important part. Clearly, the elegant 4 lines of calculus that Neyman used to derive his method are correct within the abstract mathematical theory of probability. It does lead to a computation of a probability. However, it's not clear what that probability refers to. So again and again and again and again and again, and where I'm kind of saddened is for undergraduate students. They ask a question about it, and they get smacked down instantaneously. Just understand it like this, everybody does it, don't worry about it. And that has been the attitude that I've seen. So in my classes, I saw stuff like this as well. It is what it is. But hopefully, after an hour of discussion, I've convinced you that there is a debate. The debate is ongoing, it has not gone away. So here's the example that you're studying 75% answer, you can maybe do a conditional frequentist thing, and I think that's cool. I think you should report that answer. 50% for this thing, 50% for this other thing. If I saw the same number twice, or I could tell you exactly the answer right here with probability 1. I think that's a good answer. I like that answer. Let's look at what they do. So last time we left off, and I think, since I spent a little bit too much discussing this, but I don't regret it, you won't get to the full discussion of this, but we'll pick up with a likelihood function at the beginning of next class. I asked a couple of you to write down a likelihood function, and I do that because I know it's harder to think on your toes, but this is the name of the game, and understanding the likelihood function function is going to give you a lot of insight. This is just this. fxi given theta. It's only one of those. This is fx1 given theta. fx2. IID realization. So just write that down. This problem is a little bit interesting because the probability is given to you. So what would this look like? We'll just call this P1 if we like, and P2. Probably fun to change those numbers around a little bit. They're not parameters, they're going to be given to you. But this is just going to look like this. This is going to be P1 raised to an indicator function. So indicator that x1 is equal to theta plus 1. 1 minus p to the indicator function x1 is equal to theta minus 1. So that's this. So I'm just going to say fxi given the p's, P1, P2. This is P2. I'll say 1 minus P1 right there. And theta. I have to remember to conditional. We don't really see a theta right here. What we see is an indicator, on or off. So what we need to do is we need to build that theta into this equation. Now I need to tell you that xi is an element of one of these two things, theta plus 1, theta minus 1. And I want you to stare at that equation. Where's the information about the parameters in everything? I'll just point out that these indicators right here, up in the exponent, they're only informative about things like that. How do I know? Because that's what it's entangled with in the equation. Can't pull it away from that. So these little indicators are only informative about these probabilities. So if I saw a whole bunch of realizations, I could estimate those probabilities with the sum of the indicators. That's what it would tell me. We already know the keys, so it doesn't help us to do anything. There's no info in this problem, in this part of the equation. The info is here. And so those indicators that turn on those probabilities, they don't tell us anything, because we already know the probabilities. In the traditional binomial problem, it's those indicators up in the exponents that are telling us about the probabilities. We use those in product through, we see a sum. So what a likelihood function is for this is just proportional to this thing. X. That's just x1 and x2. Essentially, this stuff doesn't help me, it's just this. So the likelihood function that we left off with last time, I'll write down x1 and x2, is proportional to, and if you'd like, we could write this in. I'll write in P1 to the indicator x1 is equal to theta plus 1. And I'll write it a little bit different. P2, the indicator x2 is equal to theta. This is x1 is equal to theta minus 1 times P1 indicator x2 is equal to theta 1. P2 indicator x2 is equal to this plus 1, theta minus 1. But I also need these indicators right here. So x1 is an element, theta plus 1, and theta minus 1. And there's an indicator. x2 is an element, theta plus 1, theta minus 1. We always say proportional to everything. So I can just go ahead and get rid of this stuff. The likelihood is the product of those two indicator functions. Theta is really defining the boundary of the space in which the data lives. It's really defining the center that ultimately defines the boundaries. And so theta is acting as a boundary condition for us. And so it's only this part that's informative to the idea. Plotting this thing, if the two realizations are different, that likelihood is a point mass on one value. And we'll go through an example. But it's a point mass on theta. That likelihood function, if I see the same value twice, is 2 point masses, equal height to each other, and they live on x1 minus 1 and x1 plus 1. So it's telling you with equal probability that that's what it is. To complete the Bayesian formulation, I need a problem. So let's pick up next time with that. And then we're going to kind of recycle everything we've done with the Poisson distribution, just to recap. And then we're going to move on. We're going to get into MCMC, Jefferys priors, more of the mathematics and computation. But I think this is an important conversation so we understand what Bayesian's goal is versus somebody else's goal. Thanks, you guys. I'll see you all on Friday. Enjoy the great weather. It's fantastic.